Hey everyone, welcome back to the channel. This is part 3 of a series regarding all things that relate to logarithms. In today's video, we're going to be going over evaluating logarithmic expressions. By the end of this video, you'll understand how to solve logarithmic expressions as well as write them in their exponential form. We'll be going over multiple example problems, including a word problem at the end. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. Alright, let's get started. Okay, so for evaluating logarithms, I kind of mentioned it in the past 2 videos, and it's not necessary for you to watch both of those for this, but it will be helpful. The main thing I want to talk about is that the logarithmic function is, or the logarithmic expression, is the inverse of the exponential expression. So what you have to say is, to what power must I raise this base, this 4, to get this value of 16? And when you say it that way, then you're like, okay, 4 to the power of what gets us 16? 4 to the power of 2 gets us 16, 4 times 4. So then it makes a lot more sense, and I think it's really important to kind of, when you're reading these problems, don't just say to yourself log 2x or whatever it is. Make sure you write and kind of say internally, and it will get easier and easier, but the more you do it, the more you'll realize how to kind of intertwine logarithms and exponential functions, and it'll be a lot more intuitive and easy to understand. So here we have a couple example problems. So they're saying express in exponential form. So again, when you have equations like this, or questions like this, and you have it in a logarithmic form, if you're saying it in its exponential form, it's very easy. So when we read this log 2, 8, we're going to say, to what power must I raise 2 to get 8? So that would be 2 to the power of 3, and that would equal 8. So that would be the exponential form. Now next, if we do log base 6, or log of root 6 of base 6, this is kind of weird, but what we're going to say here is log of 6, and then a square root can also be written as an exponent. So it can be written as 6 to the power of 1/2. 1/2 or square root, they're exactly the same thing. So now if you look here, you could say, okay, to what power must I raise 6 to get 6 to the power of 1/2? Well, that would just equal 1/2. So here you could write 6 to the power of 1/2 is equal to, you could write root 6 or 6 to the power of 1/2. It's exactly the same thing. So again, we're taking this base, and it looks a little interesting here because we're kind of getting not a different answer, right? In this case, I could have written 8 as 2 to the power of 3, but in this case, what we have over here is we don't really know what root 6 is. Like, we could do the decimal of it, but it's not going to be exact. So here we kind of look like an expression. We're saying like a is equal to a, but this is the form of this expression right here, just in exponential. So now we have log of 1 over 25 of base 5. So again, we're going to read this as, to what power must I raise 5 for me to get 1 over 25? And 1 over 25, when you have a reciprocal, you're going to note that it's going to be a negative exponent. So if I write 2 to the power of negative 3, I know that's equivalent to writing 1 over 2 to the power of 3. So for this equation, what we're going to say is 5 to the power of something is equal to 1 over 25. And again, this here would be negative 2, because this can be rewritten as 1 over 5 squared. So 5 to the negative 2 can be 1 over 5 squared. If you do 5 squared, you're going to get 25. So 5 to the power of negative 2 is equal to 1 over 25. And again, you might hear now for question. So for question D, we have log of 1 base 10 is equal to 0. And this seems kind of weird, but again, if you say it to yourself in the exponential form, if you say, to what power must I raise 10 to get 1? Well, we know that if you raise any number to the power of 0, you're going to get 1. So we can just write 10 to the power of 0 is equal to 1, and that would be the exponential form. Okay, so now we're moving on to solving for x, and this is where we're kind of manipulating the equation, or I guess, isolating the x variable. And this is something that I think a lot of people struggle with, because when you look at this expression, so if we look at log of x base 5, so to what power must I raise 5 to get x? Well, that's going to equal 3. So that's what we're looking at here. But to solve for x, it's kind of difficult, because you might think we can just go, oh, okay, well, we can do divide and be tempted to divide by log base 5. But the thing is, that isn't the inverse. And whenever we're solving for, something, or solving for x, we need to do the inverse operation of what's happening to x right now. To put an example, I could write sine of x is equal to 1/2 or something. I can't just divide by sine of x, or sine. The inverse expression is, I would do sine inverse of sine of x is equal to sine inverse of 1/2. Here, now the signs will cancel. Same thing over here. The inverse expression for a logarithmic function is, or logarithmic expression, is the exponential expression. So what I have to do is I write, okay, well if I raise both to the power of base 5, then that will cancel and I'll get this x value. So I can write x, because right here, this will cancel. This will be 1, the x comes down now. So I can write x is equal to 5 to the power of 3, and x is equal to 125. So it's really important to note that we can't just divide by things. We need to do the inverse operation to get rid of whatever function is being applied to x. Next, I'm looking at this function where I'm saying log of 27 base x now is equal to 3. So to solve for x, this is kind of interesting. So we're saying x to the power of 3 is equal to 27. That's just rewritten in exponential form. So in this case, what I would do is put to the power of 1 over 3, both sides of the equation. Now these will cancel because that'll just be x to the power of 1. X is going to be 27 cube root. Cube root of 27 is 3. So we can get x is equal to 3. Okay, now we're moving on to the example problem. So in the example problem here, we have half-life is the time it takes for half of a sample of a radioactive element to decay. The function m of t is equal to p times 1/2 to the power of t over h can be used to calculate the mass remaining if the half-life is h and the initial mass is p. And the half-life of radium is 1,620 years. So now they're saying if a laboratory has 5 grams of radium, how much will be there in 150 years? So this equation or question is kind of, a little daunting when you look at it for the first time. But what we have to note is what they said here. They said the half-life of radium is 1,620 years. So what that means is h is equal to 1620. They said right here that the half-life is h. So if we know the half-life, we know that we can just plug that variable in. So now we can rewrite this expression as m of t is equal to p times 1/2 t divided by 1620, because that's the half-life. And now what we have here is we look at this expression, we're saying this is the amount we're going to get after time t. This is the amount we initially have of this radioactive material, and it is to the power of t divided by 1620. So that would, if we kind of go through this example together, if I had the value 1620 is equal to p times 1/2, and then I put again 1620 over 1620, well, this will just be 1, because any number over itself is 1. And then I'm going to say, well, after 1,620 years, I'll have half my original amount, and that would correspond to the half-life. So now we're just being asked different kind of equations, but that's the reasoning and the rationale to why this works. So now we're looking at part A, which is saying 5 grams of radium. So that's the initial mass, that's P. And then it'll be 150 years, so that's the T value. So what we're looking for in part A is m of T. I could write m of 150 is equal to P, which is 5, times 1/2, the half-life, to the power of 150 over 1620. And now it's actually pretty simple because we're just going to solve for this value. So we're going to do 0.5 to the power of 150 divided by 1620, and then that times 5. So that would be 4.69 grams approximately of radium after 150 years. So it's barely decayed. Again, because this half-life is so long, the 150 years is really negligible in comparison to the half-life. And then it says, how many years will it take until the laboratory has 4 grams of radium? So we're starting with 5 still, but now we're trying to figure out this T. So now we're saying, what if we put a 4 value here, so that's the remaining value, or the amount that's remaining after decay. And then we're going to do 5 times 1 over 2 to the power of t, and then over 1620. So now we're solving for the t value, because that's the only thing that we don't know in this expression. And this is where kind of logarithms are going to be needed. So what we're going to do first is we're going to divide both sides by 5, because we want to go get rid of this 5 here. So over here this will be 0.8 is equal to 1/2 t to the power of 1620. So now if I take the logarithm, which is the inverse of an exponent, then I would get this t value to come down. So I'm going to take the logarithm of, I'm just going to write 0.5 instead of 1/2 of base 0.5 to both sides. So if I do that, what I'm going to get is these values in here are going to cancel. So I'll get t over 1,620 is equal to log of 0.5 of 0.8. Sorry, log of 0.8 of base 0.5. But the problem is we don't really know what this value is. We don't. If you look at it on your calculator, the only things you can take the log of base are 10 and Euler's number, so e. So here we can't actually evaluate this, but we do know a certain formula that will help us. So this change of base formula, and it states log of base a b is equal to log of c b divided by log of c of a. So here we can just change this to be a c value, and the c value is a base that we know how to calculate. So I'm going to change this part to be log of 10, and then it'll be 0.8 divided by log of 10 of 0.5. That way we can now punch this into our calculator and evaluate it. So this will be log of 0.8 divided by log of 0.5, and that is, let's see, I'm just going to write this part down first, 1620 is equal to 0.3219. Now if we solve for t, we're just going to multiply both sides by 1620. This is 521.5 years. So that is how long it takes for the radium to decay to 4 grams if the initial amount is 5 grams. That might be a little confusing, but we'll go over this logarithm rule in more detail in the next video, and we'll go over kind of how to manipulate and how to think about these equations so they make a little bit more sense. I know they're kind of daunting at the beginning, but it will get better. So I hope you guys got some value out of this video. If you did, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. If you have a specific topic you want me to cover in the future, let me know down in the comments below. Thanks again, and I'll see you guys in the next video.